So one of the more interesting applications of the free energy equation for non-standard states is it allows you to calculate equilibrium constants. So one of the things that we talked about earlier is like when delta G is negative, right? That means it's spontaneous, and when it's positive, it's non-spontaneous. And so if delta G is 0, then the reaction is at equilibrium. So basically the equation becomes this. And then instead of putting Q there, you can put in K, because the system will be at equilibrium. And then this can be arranged to be delta G of the reaction is equal to minus RT ln of K. Now, I should also point out, if you have to find the equilibrium constant at a non-standard temperature, one of the things that you can do is calculate the free energy. Oops. At a different temperature using delta H minus T delta S. And this allows us then to calculate the equilibrium constant at other temperatures. Okay, so I've rewritten the equations over here, and we're going to use these equations to calculate a couple of different things. One, we're going to calculate the standard free energy of the reaction using an equilibrium constant. And then what we're going to do is calculate the non-standard free energy under these conditions, where I have 1 atmosphere of methanol and 0.01 atmospheres of both carbon monoxide and hydrogen. Okay, so the first thing is to calculate under standard conditions. All you need is the equilibrium constant under standard conditions, and I can calculate delta G is minus R, which is again 8.314 joules per mole times Kelvin times 298 Kelvin times the natural log of the equilibrium constant, which is 2.26 times 10 to the fourth. And then I usually like keeping these in kilojoules, although you could do it in joules, doesn't really matter. But it's 1,000 joules per kilojoule, so I can get my Kelvin to cancel and my joules to cancel, and I'll be left with kilojoules. And when I do the calculation, I get negative 24.8 kilojoules per mole. So there's the standard free energy, so I should put a little naught here because it was measured from the equilibrium constant for the reaction. So I'll put RxN down here. Now, if I want to calculate it non-standard states, I actually have to know what the value is for Q. And if you remember, Q just the same form as K. So it's going to be equal to the pressure of methanol divided by the pressure of carbon monoxide times the pressure of hydrogen squared. And then I'll go ahead and plug my pressures in. So if I'm going to be doing that, because these are gases, these need to be plugged in as pressures. So 1 atmosphere at the top. And then you notice these two are the same. They're all 0.01. So that actually ends up being 0.010. I'm going to just say to the third power because they're the same. And so that ends up being 1 times 10 to the 6th as my value. Okay, so don't want to lose my negative sign. I always do for some reason. Okay, so now I'm going to calculate delta G under the conditions in C, and that'll be delta G is equal to my reaction, negative 24.8 kilojoules per mole plus again, 8.314 joules per mole times Kelvin times 298 times the natural log, ln, of, let's see, 10 to the 6th. I can't quite fit it in here, so I'm just going to write it down here. 1 times 10 to the 6th. And then I'm going to convert it over to joules. There's 1,000 joules per kilojoule. And then when I do this calculation, delta G comes out to be, let's see if we can predict real quick what might happen. Right? It was spontaneous at standard states. What happens if I decrease, at standard states means 1 atmosphere, 1 atmosphere, 1 atmosphere. But what happens if I decrease these to be less than 1 atmosphere, right? They're 0.01 atmospheres each. Then in principle, if you're thinking Le Chatelier's principle, right? In principle, it would drive the reaction towards the left. So what that means is it should become less spontaneous by lowering the concentration of the reactants. So I do the calculation, and let's see how the prediction holds. And I get 9.43 kilojoules. So what this would imply is that by lowering the concentrations to 0.01 atmospheres for both reactants, the reaction went from being spontaneous to non-spontaneous here. So basically what we predicted. Now you notice I skipped B. We did A and we did C, and I skipped B. What is the value of the free energy at equilibrium, right? This isn't actually a calculation. This is sort of a hypothetical, right? Any reaction that's at equilibrium, delta G for the reaction, it's got to be 0. Okay. So not at equilibrium, right, which would probably be non-standard concentrations, delta G for the reaction has to be equal to 0.